That, they can start. Go.
Yeah.
Yeah. So.
Okay, I've been asked to get everybody to sit down,
But I could do it remotely.
and so that we can get started. So today we've been asked by the organizers, Larry Thibos and myself, to give some insight about how aberrations are actually measured. Um, we've talked about the power of using wavefront to make corrections on the eye, to understand the optics of the eye, to understand retinal image quality and all the metrics that you can calculate from it. But we didn't talk about how these measurements are actually made and some of the liabilities. And a lot of them you'll see as we go through that it evolved. And the understanding of wavefront error, although they didn't call it that, was very, very, very early. And you'll see that in a few minutes. So we kind of laugh at each other, Larry and I. So we changed our names. I am now Ray Thibos, and Larry is Larry Applegate. So we've been in this field, since the late 90s, right? And helped with a lot with the establishment of the international standard and all the standards on how we specify things. All right, so I do consult for Wavefront Dynamics, and Larry typed this in just as we were getting ready to go. He's too old to work for a living, and he can't understand the boss's instructions. Okay, all right. And I wish to thank a good friend of mine and Larry's, Ed Sarver. He did a lot of programming in some of our illustrations. Okay, so I'm going to give an outline of the talk, and then Larry's going to say a few things, and we're just going to alternate. So to be Larry Ray, Larry Ray, Larry Ray. Okay, down the whole list of things. So what are we going to talk about? We're going to review wavefronts, thereby setting the stage for understanding how aberrometers work. I did a lot of that the other day when I was talking about wavefronts, but we're going to review it again and hopefully get it in. And there's a lot of good reasons for that. If you don't understand, and I believe Larry said this the other day, if you don't understand how these things work, you don't understand the liability. And one of my classic demonstrations of that is corneal topography. We have these wonderful corneal topography maps. And what are they specified in? Typically diopters, right? Well, how are you going to calculate a dioptric value for a ray that never crosses the optical axis? Right? And every location has tip and tilt. Right? So you should have at least two values if you want to calculate aversions there. Right? So what are corneal topography maps really good for? They're wonderful for detecting disease. That's what they were designed to do. Right? They weren't designed to tell you dioptric power, right? It was a unit made up with a bunch of assumptions so they could, as if the rays would cross the axis, and it would show you a highly aberrated eye or pellucid marginal degeneration or anything else. But quantitatively, you can't use it for optics, even though a lot of people do, but that's all buried in the software, right? To make it work, and you just don't see it. And so we're going to try to give you an idea of how these aberrometers work and the history of it, so you can make intelligent decisions as the field evolves and this becomes more and more common. Okay, we're going to talk about that, and then we're going to develop and present the basic concepts of wavefront sensing. Then we'll talk about a whole bunch of ways of doing it. And one of them is this just a classic Shiner's disc, and you'll see it's used over and over and over again, different ways. So this guy, way back, and we have pictures of all these guys, are really nice to see. All right, then we're going to develop 3 different aberrometers: the Shiner disc type aberrometers, and the Turgeon aberrometer, and then the principles of the Shack-Hartman aberrometer. And there are others, but these are the key ones. Okay, Larry, you have a few opening comments? Yeah, you can do the review, or you can offer comments.
Thanks, Ray. I'll just back up one. Well, it's lovely to see you all again. So many happy faces. Motivational time. You already had a belly full of wavefront sensors, and all of this stuff. And we're going to do this our last lesson in this one. And we're working hard really to try to educate the educators, the scientists, and the clinicians on the basic principles of this thing called aberrometry. And one of the motivations for that is 2 I can think of. The first one is, if anybody here is a clinician, is that clinicians are on an interface between scientists and technicians and the public. And it's a pretty heavy responsibility, because you have to be able to think like a scientist to understand the principles of what you're doing. And you have to be able to then instruct the technician, who might not let you use the equipment because you probably will break it if you touch the knobs. Just the same, you have to be able to make sure that they do things properly and they've interpreted the data properly. And then you have to explain all of that to the patient in words they can understand. So it's a heavy responsibility to be a doc. And that's why you're so well paid. And, anyway, so that's one of the main motivations. The other one is that, for those of you who are more basic scientists interested in visual optics, is a cardinal rule of life as a scientist that you have to, it's mandatory, there are no exceptions. You have to understand the principles of the tools you're using. You may not be able to make the tool, but you have to understand the principle by which the tool works. Otherwise, like Ray said, you're likely to make mistakes. It's quite easy to make mistakes, misinterpret the data, apply the instrument in an appropriate fashion, whatever. There's lots of ways to make mistakes. And so we want you to understand the principles. And that's why we're going to go through a big, long list of ways that aberrations have been measured. And it's a long history. It goes back to Christoph Shiner. 400 years ago, the first aberrometer was made, and then it was called the Shiner disc. We call it the Shiner disc now. So it's a long history. And there were big gaps, like 200 years later. Thomas Young used Shiner's disc to discover astigmatism. And then another 100 years went by before a guy by the name of Hartman said, oh, instead of having a disc with just 2 holes in it, how about we have like 100 holes and so on. So he developed and now you're in a privileged position to be able to have the technology at your disposal. You press that button and you measure aberration for 1,000 points in the eye's pupil, and the computer does everything. And you might think that the computer is perfect, but there are pitfalls, and they're made by humans and they're used by humans, and there are lots of ways to make a mistake. Okay, so I'm going to start with reviewing a couple of the concepts that we've already touched upon. And the first one is about the connection between wavefronts and rays. We always give credit to Christian Huygens, great Dutch scientist from the early 1600s, for having conceived in some way. But I don't know how he did it. I've never read his original papers. I really need to do that. When you're retired, you get to do stuff just because it's fun, not because anybody says you have to do that. He probably wrote in Latin, and I'll have to get Google translation tools to translate for me. But or maybe somebody's translated it into English. I'd still like to know how he had the insight to realize that light might be propagating as a wave. Most of us think that he probably did it by analogy with water waves. Water waves are a bit simpler because they're on a 2-dimensional plane, not a 3-dimensional space. And then you have a nice smooth pond, You take a pebble, you toss it into the middle of the pond, and you can see the waves just expanding. And energy is being transmitted from where the rock fell in to where the water hits the shore. That's a transmission of energy over a distance, and that's pretty amazing stuff. And maybe that's the way light works. But I think it goes deeper than that. I suspect that he used not just one pebble, he probably threw two pebbles into the string, a little bit separated, so you can make two expanding rings going out. And what happens when those rings collide? Well, the peak of one and the trough of the other might annihilate each other, leave the water perfectly flat. Or the two troughs might reinforce, or the two peaks might reinforce, and the wave is bigger than it had been from either stone alone. Well, that's the concept of interference. I mean, like, he invented physical optics in a water domain, if that's what he really did. And then there's this other amazing thing that he did, was to imagine, as Ray told us the other day, that every point on this wavefront propagating in a certain direction could be conceived as a little point source radiating out little spheres in itself. And in this point, little spheres, and this point, little spheres, and they all, I should have done it down here, so that when they all add together and you move downstream a little bit, lo and behold, you have another perfect wave. See, well, how do you ever imagine that you could take a whole bunch of little waves, add them up, and you have a new wave? And that's incredible. But I think there's a good water analogy. If you ever do this sometime, take a handful of pebbles on a still pond and chuck them into the water, and you'll get a multitude of little, or watch raindrops. That sometimes works too. And you see a multitude of expanding waves, and close to the location of where you threw them into with your pebbles, there'll be chaos. There's up and down. It's just a chaotic sort of movement. But just watch the water propagate just a little bit, and you'll see that, lo and behold, you have a nice spherical expanding wave again. So, well, that shows you that with a little imagination and a little demonstration and some analogy making, you can see how a wavefront can propagate by having lots of little wavefronts being all added together in a constructive sort of way. So my bet is that's how he came up with it. But in any event, we give him credit for the concept of light that's being propagated as waves. But what about rays? Have you ever heard of a water ray? I've heard of light rays. Have you ever heard of a water ray? I mean, you could take a hose maybe and blow a stream of water out. Maybe you think that's a ray, but it doesn't go on a straight line. It flies a parabolic trajectory under the influence of gravity. No, I've never heard anybody call that a ray. Maybe so, but it's quite remarkable that he didn't think of rays, but he did think of waves. Mm-hmm. And then you get to the next diagram, which Ray has finally generated for us, to think in the three-dimensional sense of light waves expanding out as a sphere. But who amongst us has ever seen a spherical wave of light? Never experienced that in everyday life. Oh, but you say, oh, but I do experience rays. Everybody can see a ray of light. I'll take, put a hole in that curtain and the sunshine comes in. Just, if the room is a bit dusty, you have to have a little bit of dust in here. Since the light by itself, you wouldn't be able to see it. It's got to hit something, scatter the light. But if we had a dusty sort of room and a hole in the curtain, you see a ray of light shooting through here like this. You say, oh, light propagates as rays. Well, forget it. Oh, you guys know waves? Who's ever seen a wave? Never seen a wave. So at some point, the two ideas came together and said, well, if light is propagating as a wave and the ray shows you the direction of propagation of that wave, maybe rays and waves are just two ways of describing the same thing. And when it's appropriate to think of light as a wave, great. Think of it as a wave. And when it's appropriate to think of it as a ray, as we do in geometrical optics, think of it as a ray. It's the same phenomenon, two ways of describing the same thing. And a good deal of aberrometry is thinking about rays, but we use the results to interpret what the waves must be doing, even though we can't actually see the waves themselves. Okay, so we imagine a point source of light. You might think a whole lot of waves are coming in. At the distant point source, lots of waves are being generated, and they start out as spheres, but if you let them propagate long enough, a sphere will begin to look an awful lot like a plane because it's got such a big radius of curvature. So we got some plane waves from light very, very far away, maybe Alpha Centauri up there in the sky. And at the same time, we control rays as if they were coming in, thinking about ray propagation instead of wavefront propagation. They're both complementary views of the same thing, but the key thing to remember is that they are always perpendicular to each other. Even if the wavefront is curved, like this wavefront has been curved because it's been through a lens, the ray is always perpendicular to the wavefront. I think I just said about everything that was in that slide. Yeah. And the wavefront's aperture fraction, if it was a perfect lens, the wavefronts would be a sphere. Now, what this diagram does not show you is the effects of diffraction. As Ray explained to us in his lecture the other day, if you had a really, really big lens to transmit a really big chunk of that wavefront, that'd have to be infinitely big if you really want to be fussy about it, then you could get a spherical wavefront. But as soon as you put up an aperture, you're blocking some of the light that was required to produce a spherical wavefront. You've blocked off some of those little hanging wavelets. They're not contributing anymore. And therefore, the final result can't be a perfect sphere. But we draw it as if it is for the purposes of argumentation. And so we imagine these light rays are going to come in, the wavefront's going to come in, the waves collapse to a single point, all the rays meet in a single point. It's an idealization of reality. And if you allow diffraction into the equation here, then this is not a tiny infinitesimally small point. It's distributed in space a little bit in a way that George Airy said it was going to have to be, called Airy's disk. So we're going to think about wavefront devices for measuring wavefront aberrations. The key principle is going to be used is that we're going to take this extensive wave front and break it up into lots of little pieces. And every little piece, although it's slightly curved, we're going to pretend that it is flat. That's an underlying assumption. It is as if you drew a tangent plane to that curved surface. We're going to take a little piece of that tangent plane. And every place on that surface, it'll be a different tangent plane because every point has a different slope. And then once you get it down to being a plane, a tiny little segment of a plane, there's only two movements that are necessary to describe its orientation. That's tip and tilt. And that's what aberrometers in the end tend to do. They just measure the tip and tilt of every little point on the wavefront that you care to analyze. Oops, back up there. So here's that famous diagram now showing how wavefront error is going to be defined as the difference between an ideal wavefront and the actual wavefront. And we want to know this distance. Well, like I said yesterday, you can't get a ruler in there to measure it. But what we're going to be able to do is to measure its slope. And we're going to do it in a way that's reverse from what this diagram shows. Instead of letting the light come into the eye, we're going to objectively, for objective aberrometers, we're going to let it fall out of the eye. But there are subjective aberrometers, I'll mention those too, and which this is a pretty accurate description, but it's going to be based on where do all these aberrated rays end up? Remember, that's what we call the transverse aberrations in geometric optics. They're in the image plane. And if we know where all those aberrated rays ended up, we can work our way back here using a bit of geometry to figure out what the slope of that wavefront was. And in fact, we argued, or I argued anyway, and I hope you believe me, is that the slope of that wavefront error function, no, it's not that one, it's not that one either. It's the difference between the two. That's the wavefront aberration. It's the difference between these two. It's not actually on the diagram here, but you have to imagine another curve that is the difference between those two. And it's the slope of that difference function, that wavefront error, that is equal to the angular distribution of these points in the image plane. That connects for us the retinal plane to the pupil plane. And it's some of the methods actually measure where these points are located. So the key point to remember, rays of any location on a wavefront are perpendicular to the wavefront, and it doesn't matter if it's perfect or aberrated, that rule can't be violated. So that's setting the stage, hopefully, for understanding how aberrators work. And Professor Ray is going to develop and present the basic concepts of wavefront sensing. And we're going to do trade-offs. He's going to do one question, I'm going to do the other. If he makes any mistakes, I'll be sure to correct him. And if I make a mistake, he'll correct me. And that should work. But beware, if we actually agree,
That would be very
then
strange.
probably you should be suspicious. We're probably missing something.
Yes, Larry and I are famous for arguing a point beyond the need. Okay, we're gonna go on now. So just to remind you, here we got some rays coming towards a refracting surface. You can imagine that surface to be anything you want, okay? So we take one ray and, oh, it behaved really nicely. It went nicely through. And we take another ray. Oh, it didn't even cross the first ray. Take another ray. Oh, hey, all the principles of geometric optics were just violated. How do we calculate a diopter now? No, it never crossed a reference ray. Okay, so we're going to capitalize on that. We're going to figure out, just like Larry said, where each of these rays struck a reference surface. And what's the reference surface? The retina, right? That's what we're interested in, is where do those rays hit the retina? All right, so let's do it again. I just put an image plane in, but consider it the retinal plane. All right, so here come the rays again. Got this refracting surface. Here comes a ray. Oh, struck right there. We'll call that the reference ray. Call it the fovea, right? And then that's where the other rays. Now, the trick, what makes it work, is if we knew the XY distance of each of these errant rays. Once we know that, we can calculate the slopes, and from the slopes, we can calculate the wavefront here. All right? Larry does all the math. I'm going to give you the concepts, okay? All right. So what we're going to do is look at the delta X and the delta Y, the air in two directions, tip and tilt. Right, back to that fundamental concept, tip and tilt. All right, so that's the basic principle going on, and now we're going to start talking about the various aberrometers that existed. And the very first guy that really discovered it was a scribe, Shiner. How did they? What did scribes do? They made new Bibles. And he's working by candlelight, right? He got bored. And he punched two holes in a piece of paper. Well, actually, just one hole, and started moving it around. And, wait a minute. Punched another hole in it. Goes, hey, I see two candles. The rays were hitting different places of the retina. And Larry's going to show you exactly how that works.
Right. So I get to talk about Shiner. He's one of my scientific heroes. Shiner was a great guy. He lived in the late 1500s, early 1600s, and he wrote one of the first textbooks in the optics of the eye. It's called Oculus. He wrote it in Latin. There is a picture of him. And he was a Jesuit priest. In those days, Jesuit priests were some of the most influential scientists and philosophers of their age. Maybe they just had a lot of time to think and do experiments. I don't know why the priesthood supported that kind of a man, but he was a very good experimentalist, and he was the first person to discover or show evidence, objective evidence, that the retinal image is where so the retina is where the image that is responsible for perception. That's where it occurs. See, before Shiner, there are all kinds of really weird ideas going out there, like the lens itself was the seat of vision. Light came in, hit the lens, and made the one wiggle, so wiggling lenses, and that was going to lead to perception somehow. All kinds of strange ideas. What Shiner did, just threw all that stuff away. That's some nonsense. He took a sheep's eye from the abattoir, took it out, dissected it, took away some of the sclera on the backside, and then took it outside, pointed at some brightly illuminated scene, and looked at the back end on the backside. And without the sclera in place, the retinal tissue, the fundus is reasonably semi-transparent. It's opaque enough, scatter-light enough that you can actually see the image from the backside. And you can see the image being formed. And lo and behold, of course, no surprise to him, the image was, of course, inverted. And the fact that it was inverted through all kinds of philosophers, they got their knickers in a twist. It can't be the retinal image that matters. Look, it's upside down. We see upside up. We don't see upside down. That's not right. That's not where it is. And so they went back, and everything was wrong for another 100 years, thinking incorrectly until guys like Kepler and Descartes sort of straightened things out again. Anyway, he's a really good guy. And one of the basic issues he has is, well, some people are short-sighted. How can we measure where their far point is? So he invented the Shiner disc. Very clever and simple. He couldn't get anything simpler. He took like a piece of paper or parchment paper or whatever, some old pink flat thing, and poured 2 holes in it. And then set up on the table a candle. There's the candle, and he said, okay, now hold that little disc up on your eye. Actually, it's just 2 points now in the pupil. And you look at the candle. What do you see? Oh, well, I see 2 candles. So really, that's interesting. 2 candles. Back up a little bit. Oh, what do you see now? Oh, those 2 candles are getting closer together. Well, back up some more. Okay, now what? There's only 1 candle. Isn't that remarkable? That's my far point. Couldn't be easier. So you measure the spherical refractive error with a non-electronic. You don't even need a computer. It's just a simple piece of paper with 2 holes in it. And if you back up even further, of course, then they start to separate again. So you get this symmetric hyperopic or myopic blur. And if you get it just right, those 2 points line up. That's because that's how the rays have come together. Otherwise, you would have had rays that are separated. See, we got an example here. Where he came in, that was one of the candles you perceived. This is the other candle you perceive. There were 2 candles. Okay? That's because those rays are not coming from the far point. So in a diagram like this, draw some rays as they proceed through the nodal point. We do that because the nodal point is the line along which you can project any point on the retina out into object space and imagine where that object would have been had it been going in a straight line. So although the light ray came in this way, when it got refracted, it ended up down here, and the person perceives it out there and says, ooh, there are 2 candles, candle number 1 and candle number 2. That's because those rays did not intersect on the retina. Wrong button. For a hyperopic eye, it's a similar sort of diagram, except now the ray is not bent enough. And so again, you'll have 2 points which projected out in object space produce the 2-candle sensation perception. Now, here's the clever bit, is that that was 1619 that Shiner published his treatise on the optics of the eye, and he described that simple device. Almost 200 years passed before Thomas Young, the famous Thomas Young, Englishman or Scotsman, whatever he was, I forget, used Shiner's disc, and all he did was to rotate it. So he found out my far point when the 2 little holes are vertically oriented, and then he rotated. He said, guess what? That's not my far point anymore. Now they're coming together. Aha! Here's my far point when the rays come in horizontally displaced from one another. Guess what? The interval from here to here is the interval of astigmatism. We call it Sturm's interval. And halfway between is what you want to call the spherical equivalent. But I've already told you you're not allowed to say equivalent because it's not equivalent. And putting here is neither that far point nor this far point. It's just something in between. It's the average. So it's the mean, but it's not an equivalent. So that's the mean sphere. So in a stroke, good old Thomas Young invented astigmatism, and essentially even people that were working in the optics field outside of vision had never really captured the essence of astigmatism. So Thomas Young gets credit for actually discovering astigmatism and naming it astigmatism, means not stigmatic. The light is not going to come to a single far point. So Shiner gets credit for all of that. And that's the principle that was used for a number of years. When I was fussing around with this stuff back in the 1980s, some time ago, because we did not yet have objective aberrometers available, hadn't been really developed as a technology, even in research labs. So you can do the same experiment that Shiner did. You just have to have a lot of holes and maybe do them 2 at a time and measure lots and lots of places on the pupil, not just 2 places. And Rob Webb, one of our favorite colleagues from those days, a very clever and inventive man, developed a commercial instrument to do just this. Other people had used it in the research labs. So they called it the spatially resolved refractometer. It's a nice fancy name. Now imagine we're going to use basically like a Shiner's disc kind of thing to isolate 2 rays, see where they go. And basically Shiner's principle was he changed the location of the source from being way out there a long ways away, brought it in till it's about here. And now when that ray comes in, guess what? It's going to end up in the same place as the reference ray. And they've come to coincide. So they call it the coincidence refractometer. And that's what Shiner did 300 years before, or 400 years before. But Rob Webb got it patented because they didn't do patents in those days. Another example. The point is to remind you, if you could look at the back of the eye and use Shiner's technique of dissecting away some of that sclera, you'd be able to observe the 2 locations, one for the reference ray, one for the aberrated ray. And to tell you the truth, when I was developing an aberrometer in my lab some years ago, I made a model eye, physical model eye, that was just like that. There was a glass sphere, itched the edge to make it scatter light a little bit, and then put it into our aberrometer, made the aberrometer do its thing, and you can see the little dot moving all around the backside. It was a nice little toy that showed us that the instrument was working as it was supposed to be. It was a scanning aberrometer. And so you move that by moving that object point, so axially, you can make this point down here, move up to there, and they coincide. You say stop. That angle there is the slope of the wavefront error function. But we've measured it. We measured it in object space, because you have to. You can't get a probe inside the eye. We've measured it in object space, but we infer that that was exactly the same angle we would have gotten had we done it the other way around, where we measured the angular deviation of this ray from a common point source. One of our colleagues from Europe, Professor Malamy, developed a commercial aberrometer, and they use exactly the same principle called a Tracy ray tracing aberrometer. Uses that same principle, and in his case, what he does is introduce a laser beam through a beam splitter here. So the laser beam comes in; they're all going to be parallel to each other. But the laser beam is going to enter the eye at some location. This is just a cross section. You could be out here too, anywhere in three-dimensional space, anywhere in the pupil. And then the laser beam is going to go in, and then it's going to land someplace because it's aberrated, right? And he wants to know where that ended up. But it's not a subjective thing where you've got a person saying, "Oh, I see 2 points coinciding or coming together to a single point." This is an objective instrument. And so the objective instrument has to measure where that spot is compared to the reference. So what does he do? He lets the light come back out through a beam splitter, and he puts a fundus camera up there, a detector, a camera that's focused on the retina. And that camera can see that there are two spots, because there's the reference spot and there's the displaced spot. And it needs to know the angle between those two. Because that is, as we said yesterday, that's the slope of the wavefront error function. So if you do that many, many times, and you have the spot going in lots and lots and lots of different places, but only one at a time, just one at a time, it goes around, and the retinal spot diagram, which, depending on the trajectory, if I do so it's got a little shutter in there, some mirrors that are moving the laser beam around. And so the spot goes from there to there, to there, to there, to there, to there, to there. It's taking these pictures, and the whole thing happens really fast, a few seconds, and you've got a whole collection of spots in this spot diagram. And they are, if you want to calibrate these axes, these are listed here in microns, because that's the kind of retinal distance. But remember, each micron's worth a certain amount of an angle, and forget the actual calibration, but if your camera is well calibrated for angles, then you end up with a measure of the eye's transverse aberrations as a function of angle in both x and y. And that's the slope. That's the wavefront slope at each point of the entry beam of that laser beam. So we've got wavefront slopes. You say, well, what good is wavefront slopes? Well, if you remember from yesterday's lesson, you can almost start right there and do lots and lots of interesting geometrical optics just knowing the wavefront slopes. But if you really want to go back and find the wavefront error function, you have to integrate those slopes to get a proper wavefront error function. And some people do that just for the fun of it. Some instruments do that. And then when are they going to go to use it? What do they do? They differentiate the wavefront aberration function to get back to slopes. In a sense, you didn't really have to go to all that effort. You could have just stayed with the slopes. And in fact, it's possible to fit slopes with Zernike polynomials too. I didn't mention that, but you can't do that. And you never ever have to measure the wavefront error function. Come on. Oh, there we are. I think I've said everything I wanted to say about Shiner disk. So you talked about Mr. Schering, another famous man from the olden days.
Okay, so I'd like to just make a couple additions to what Larry said, because they're just interesting additions, not anything. So I'll back up a couple. And Vasil Molivny is Russian, and he worked for the Defense Department, right?
He's Ukrainian.
Oh, I'm sorry. I should be
Big
very
difference.
careful about that. And I was properly, he's Ukrainian and he's very unhappy. He lives in the United States right now. So thank you, Jess. I really appreciate that correction. But one other thing I wanted to point out is, so he said, oh, if you just want to measure little distances in X and Y, it's really easy. I have a quadrant detector, right? And I know that I want that dot to be represented in the center. All I have to do is calculate how much I had to change the angle to move that dot to the center. Guess what? He was at the head of the missile program. I have a target I want to hit. That's the center of the cross, and the missile corrects all the time as it's flying through the air to hit its target. So he said, I know all about this. I can do this. I can do it for you, because all I have to know is where you want to go, and I'll calculate the air for you. I thought that's just an interesting addition, so that you know that. And then on Rob Webb's, I'll go back there real quick. So this gentleman, as Larry pointed out, is a very, very intelligent man. He takes concepts and builds them into instruments, right? And what I wanted to point out, the difference between the two, the subject had to answer the question here. He was manipulating mirrors to get the angle necessary to bring it back to the reference. And so the subject had a joystick. And so it took a long time to measure the aberrations of the eye. It wasn't fast, right? And so Molivny's contribution was, I can do it pretty fast. Even though I'm sampling one at a time, I can get this all done in a second if I'm only doing 28, 29, 30 points. Okay, so let's get back. So now I'm going to go on. So we're going to get faster and faster and faster in measuring wavefront error. All right, that's one of the concepts I wanted to get developed here. So there's this gentleman named Hartman. That's this guy up here. And he lived a while back too, but we're getting more and more modern, as you noticed. And telescopes were coming along nicely. But they had optical errors, right? Not just sphere and cylinder, right? They had other optical errors. And Hartman was very smart. He said, well, let's just put some holes in front of the lens and see where each of these rays are going. And then we're going to polish this lens so it goes to the right place. We're going to correct X and Y again. And if you ever get the opportunity to go out to the University of Arizona, a good colleague of ours, Jim Schwierling, lived out there. And he would have, well, he passed now, but he would take visiting scientists over to where they make the 10-meter mirrors, which is a lot of fun to see, right? And then they make this big vat of glass, and they spin it, right? And it makes a parabola. Molded glass makes a parabola. Turn off the heaters and let it, while it's spinning, let it cool down. And then you have this big mirror, right? But does it have aberrations? They haul this big mirror over to the football stadium, right? And they would direct a laser beam, just move it over, move it right over, and hit the mirror. And if the reflection didn't go to the right spot, here comes a little polisher, changes the slope in that location until it goes to the right place. Okay, and that's a Hartman screen. Just think of it as Hartman screen. It's a laser now, but I'm sampling one point. So Hartman was very clever. He said, let's use lots of holes. All right, and then Turgeon realized that if you use a Hartman screen and stuff, then, whoops, I went the wrong way. We could just put this Hartman screen up, and then we have all the points down there, right? But there was a problem. They were all too close to each other, and you couldn't differentiate or know exactly which ray was associated with which entry point, right? So he said, well, what do we do here? We put a aberroscope lens in. We put a lens in with known aberrations, big positive lens, right? And we're just going to spread everything out on the retina. So here come the rays. And now the aberrations are still there. We just moved what used to be focused on the retina out here and allow all these things to diverge. So now they're all over in 3 dimensions. I'm sorry, 2 dimensions on the retina. All right. So how does this type of aberrometer work? So you have your Hartmann screen, you have your aberoscope lens, right? And then you're going to pass light through it. You have all the points on the retina. Then you're going to look at each of those points with a camera. As light comes back out, hits this beam splitter, goes up to a camera, and you take a picture, and you know where you want the spots to be, and you know where the spots went. Now you can do delta X, delta Y, get all the transverse aberrations, and calculate the slopes as Larry's pointed out. So you can get all the information you want. And there's quite a few aberrometers that were basically on this principle. Okay, so here's a cartoon of it. So you have your Hartmann screen, known grid of holes. You have your aberoscope lens, goes into the eye, forms this dot pattern on the back, comes back out, hits a beam splitter, take a picture of it, send it to the computer, calculate the wavefront angle. Okay, so now we're going to move on to the Hartmann Shack aberrometers. Many aberrometers work on this principle, and you'll see why here with Dr. Thibos taking over here. Oh, I'm sorry, Larry Applegate.
I knew you were going to finish my sentence. Okay, so a couple of things that Professor Applegate did not mention. Let me back up. There's a problem in this technology, even though it's super fast because you do all the spots at the same time. You have what's called the correspondence problem. Which of these dots corresponds to, let's say, that one? That's where the hole was, but which of these many spots corresponds to that one? That can be kind of tricky figuring it out, especially if these dots move a lot because there's lots of aberrations. Have a correspondence problem. Now, so we've got the same problem when it gets to the Hartmann Shack sensor, but it's a sort of a fundamental problem with this kind of technology. It's quick. The Tracy aberrometer didn't have that problem because it only had one spot at a time. There was never any question about which spot belongs to which laser entry position. But with this kind of simultaneous device, you have a potential problem. So the more modern version now, and who knows, a few years from now, it might be something much, much better. The king is still the Hartmann Shack aberrometer. Shack is a vision scientist, an American, worked at the University of Arizona, Roland Shack. And one point he pointed out was that the Hartmann screen had been around since early 1900s. It's been used in the optical industry for a long time. But it's rather inefficient because, these are the holes, but a lot of your light is being blocked by this opaque disc. You're losing light. And that's important for the eye, not so much important in physical optics or optical industry, but for the eye, we're light limited. We can't just put an arbitrary amount of light into an eye without causing damage. So for safety's sake, we have to be as efficient as we can be. And that's where Mr. Roland Shack came in. He wasn't actually interested in the eye so much, but he understood the problem with efficiency. And so he said, let's make a different kind of Hartmann screen. That's Roland Shack up there. I got a picture of it here. Well, not just yet, but you'll see in a moment what his machine looks like. So here we are, a view once again of that famous picture of the eye with a laser beam is going to be put onto the retina here. We're going to have all these wonderful expanding wavefronts, and then they go through all that aberrated optical apparatus. If it was perfect, the rays would come out parallel, but in fact, they're not. So what have I got here? Here comes the slow-mo version of the rays coming back out through just one of the holes. If only there was a far, and you know now that that ray may not intersect. Right? If it's a skew ray, it's not going to intersect that far point. But for simplicity's sake, we think it is. We show it as if it were. And what we're going to try to do is to measure this entire wavefront that's coming out of the eye now, using basically the Hartmann technique, but a different kind of Hartmann screen. That's the Hartmann screen that will allow us to measure the angular deviation of the actual ray from where it's supposed to go. And that's the slope of the wavefront error function, that angle is. One more time here. There's a nice aberrated ray. And what happens when it hits a lenslet array? This is the fancy new version of a Hartmann screen. And what it is, it's a whole bunch of little lenses. Instead of having just opaque holes in an opaque background, there's no loss of efficiency. All the lens being used, but only a little piece of it. Each lenslet picks up just a little piece of the light from this aberrated wavefront. Going to break that wavefront up into lots and lots of little pieces. And each little piece then is going to be collected by that ray, by that lens. It's going to come to a focus someplace, and with a click of a button, you get a picture that looks like that. That's the data image from which you're going to infer the wavefront slopes. That's actually a pretty good image to show you what the things that can go wrong. You recognize what's going on here? I don't know, I might have actually tried this image myself. I don't remember where it came from. But look, there's a funny kind of reach right in there. We saw that quite a bit when we were playing with making measurements of eyes. It tended to be Asian eyes. And they kind of have a pretty powerful upper lid, whatever the proper word is for lid. And what's it, is it toast or something? Is that the name of the clinical term, or a lid that kind of drops down a little bit and constantly presses against the cornea and pushes it in, and the cornea is kind of dented a little bit on the upper half. So you ask them, they say, you're going to your subject in there and say, oh, you can't see the top half of that. Open your eye a bit further, pull way up, and you get to see the whole pupil. And by golly, some of these spots are really crammed together, really close together, and maybe you're not quite sure which lenslet produced which spot. So one of the techniques that the instrument manufacturers use, they put what's called range limiting aperture. It prevents spots moving too far. So it's got a limited dynamic range for that reason, but at least it doesn't get confused. Another potential mistake people made, and I've had colleagues who've had this problem, is that without special instruction that the subject should open their lids as far as possible, kind of droops down a little bit, and this is actually covered by the lid. So the pupil, when you look in, it's now circular. The part of the pupil the instrument can see is a piece of a circle. It's not the whole circle. See? Now, as you know, that the really beginning of analyzing these kind of data is to say, where is the center of the pupil? Well, if all you have to work with is the bottom 2/3 of this picture, you might think that the center of the pupil's down there. All right? And you make a mistake. That's not where the center of the pupil is. The center of the pupil's up here. That's the kind of mistake that you could make if you didn't understand the principles of what we're doing here and trying to make measurements of these aberrations. Or you might make the argument, well, that's okay if the habitual position of the lid is such that I don't actually have a circular pupil. I've got some kind of an elongated, oval sort of nebulous face. Now what do I do? Huh? And the instrument's got to be clever enough to do what you want it to do. Couple ways to handle that. One is you might shrink the analysis pupil down. They often have a command on the instrument. It says, where would you like the pupil analysis pupil be? And we'll just get rid of all the other dots, just center on maybe just this little piece right there. Say, I can get a circle in there. Let's use that one. You know, you might choose to do that. But then you're ignoring these data up there, and those data too, they count. For vision, they'll count. See? Or another way to deal with it is to have a second camera that actually takes a picture of the pinner's pupil. And see, many of these aberrometers, they estimate the pupil's diameter and location based on this image. But that's kind of illogical because all those little spots have moved. Huh? Those spots have been moving around because of aberrations. You're going to get an aberrated sense of how big the pupil is and where it's centered. It seems like it's all wrong. I think that's a bad design. And some of the early aberrometers made that kind of error. The more modern version will actually have a second camera that takes a picture of the iris. And now it says, okay, now we know where the pupil is. The iris camera tells us, and it's got to be well registered with the data camera so the spots can be overlaid on top of the actual pupil of the iris. And now you've got a more reliable machine. One of those potential problems that you can spot if you understand the principles of what we're doing here. So we have the device in the end looks a bit like this. There's a laser and a beam splitter that allows you to put a point source on the retina, and that light's going to come zooming out. And they use some relay lenses, often a little telescope, to effectively put this lenslet array optically is back here in the pupil plane. You can think of it that way. Optically, those two are conjugate. This plane of the lenses is conjugate to the plane of the pupil. It is as if you open up the eye and you put that little lens right there in the pupil plane where it's supposed to be. That's where you want to make your measurements. And that telescope does that for you. Telescope can do other things too. It can also magnify the data image a little bit, maybe give you better resolution as an option. And you end up with a data picture like that. The ideal location of all these points, of course, is a perfect grid. That's part of the calibration device, a calibration procedure of the instrument. And then in the end, you have the spots wherever they went. Interesting image. Notice there is no spot here. That square doesn't have a spot. Yeah. Why not? Depends on how the instrument's designed. It's possible that the spot that was supposed to be in that square moved over here. It moved so far, it moved out of its box and landed up over there. So this is part of the correspondence problems. How do I know which spot corresponds to that location? And so some of the instruments are designed to make sure that if a spot goes so far that it's going to interfere with the measurement of the neighboring spot, we'll just cut it out, get rid of it. Don't even bother with it. One of the very first Hartmann-Schenck systems built that way. So in the end, we're measuring the slope of a tiny little piece of the aberrated wavefront, and its position is a summary here. And it can change both horizontally and vertically. And that gives us tip and tilt of the wavefront, the two slopes, horizontal and vertical slopes. So each lenslet image, its displacement from the ideal position determines the local slope of the aberrated wavefront, following the reconstruction of the wavefront error. Some of the instruments don't like dealing with fuzzy data, so they do a little bit of image manipulation, like putting a threshold Because the deal now is you just have to find where the spot is. That's all you care about. Where did it move? What's its location? And if there's a lot of haze, you might have seen that in some of the other pictures. There's a lot of haze around it, kind of interfering. Was that previous picture? This one. This is a particularly good example of a horrible data image. You think, well, where are the spots? And I have no idea. Maybe it's from a cataract patient. I don't know where it came from. But it's a pretty ugly looking spot picture. And you say, well, I got to find out where these spots are. So you do some fancy image processing. Depending on whether or not that was a well-designed procedure, you may or may not have errors introduced into your data. Well, this example could show you that possibility. But in the end, you look for an array of spots, where they're located, compared to the ideal pattern, and then the analysis proceeds from there. Now, this is an example of a really high resolution aberrometer. There's lots and lots of spots. Ray says he's getting thousands of spots now. It's a very high resolution instrument that allows you to measure. In principle, that means, in principle, it's just like a Fourier analysis. One measurement spot gives you one Zernike coefficient. There's like one Fourier coefficient, same idea. So if you had 100 spots, you could do 100 Zernike coefficients. I don't know anybody that goes up to 100 Zernike coefficients. That's a lot. But with 1,000, you mentioned the equation of the Zernike polynomial for the 1,000th Zernike fit. It would take the whole blackboard just to write the equation and be a monster. I don't think too many people do that. But the idea is that with having an overdetermined system, we have lots and lots and lots of data being fit to just a few, maybe 10 or 15 Zernike polynomials. Then you're making a statistically robust kind of least squares estimate by Zernike analysis. Aren't you glad you learned all about analysis? And you get the jargon. You understand the terminology, the jargon, the basic principles of mathematics to get a really nice picture of the wavefront. Dan Neal was the designer of the first commercial aberrometer, went on the market in the year 2000. That's 25 years ago. There's been lots of devices since then. Dan was a good colleague of ours and helped us understand how these instruments work. So that's what you call outgoing aberrometry. It's an objective method as opposed to the subjective method that Ray talked about. So really just to close our session here with comments on what to look for when if you want to find one of these instruments and make use of it.
Okay, Larry made some really wonderful points that I'd like to reiterate. Because if you do get into wavefront sensing, you have to make a decision whether the data is good or not, okay? Because the machine's going to do what it does, and it's going to give you an answer. And if the data is bad, then you're going to get a bad answer. Okay, so let's go just back a minute to this figure. And so what I would strongly recommend, if your aberrometer doesn't show you this pattern, this is the fundamental data. Okay, this is what's being used. And if you look at it, like Larry pointed out with the Asian eye, and I have to give a real compliment to Larry here because this is my teaching slide set, and Larry agreed to alternate with me, and he really he did a fantastic job of coming up with exactly what I would have said if I were doing the slides. But what I would like to emphasize again is if you can't look at this pattern or train your technician to look at it, when it's bad, and they have to take a new image, then you're dealing with bad data. And as Larry said, it's really important to have a separate camera telling you what the pupil really looks like, right? That's really important. In it. I want to go back one more slide with the picture. Oh, no, I want to get to Dan Neal, wrong way. Dan Neal is he's been a very good colleague of all of us in this industry. But he built the first really good one, right? Hartman Jack wavefront sensor. And what happens when you have a small company? Big company comes in and says, I want you, and makes an offer to the company, and they go, all right, we'll sell, right? And it got swallowed up by several different companies, eventually went to Alcon. And Dan couldn't invent anymore. He's an inventor. And so his life was altered for a while he was under contract not to do anything else because they paid him a lot of money, right? And now he's making new aberrometers, and that's his. Okay, so a little history there. Okay, outline of key features to look for. Well, this one gets me in trouble, okay, because you start talking about what a good aberrometer is, and that rules out some aberrometers, right? And people don't like you when you rule out their machine. So I'm going to try to talk about it generically. Okay, so how to pick an ophthalmic aberrometer that is best for you? Well, it depends on what your goal is. Ophthalmic aberrometers can be used for many purposes. It's not easy to easy question to answer and can easily raise the ire of those with vested interest. So, however, in general, low sampling aberrometers can be precise. They can be very repeatable, but risk sacrificing as accuracy by undersampling. As Larry pointed out, if you have lots and lots of samples, even though you're going to only fit to maybe the 5th order or 6th order Zernike, right? Then you have a much more accurate, you have a way to estimate the error that your aberrometer is doing. And so if you want accuracy, then you want more sampling, right? If you just wanted to detect aberrations, then you just have to sample, like Larry said, you need maybe 20, 30 points, and you can get a 4th or 5th order estimate from the Zernikes. Okay, so another issue is dynamic range. As Larry pointed out, if things start crossing over and stuff, then you get in trouble. So aberrometers put in a limiting aperture that prevents the crossover. But if you have high aberrations, there's going to be crossover. So you have to develop a specialized device that has very short lenslet focal lengths. So that you have to decide what it is you want to do. But if you want to fit these contact lenses, and I think the industry will move towards it because it really helps these guys. All right, I think that's it. We'll see if there's anything else that comes up. Nope, thank you. And questions.
Thank you very much. I wish I had this talk 20 years ago, then I would have understood so much more. And just for clarification, so the light goes through and simultaneously it comes out. So what if there is, so I want to say in patients with cataracts where there's specific opacities, that will be a problem, that will
Yes.
pose a problem.
Yes.
And also, this is so, and you've measured the amount of hertz it moves with. If there is micro movements of the tissue due to pulsation or anything, does that play a role in the aberration in the end? Because this is really the deviation of the light from the original spot. So, and it's measures in microns. So it's such a small measurement. So small breathing patterns or anything can influence this, or pulsation or vessels can influence it. Does it play a role in the measurements? Thank you.
Yeah. Okay, so I saw several questions in there, and I'll make sure that I answer them. Also, stop me if I don't. So you're absolutely right. One of my pet peeves, okay, and Larry and I disagree on this one, okay, and Larry can chime in a minute. One of the things that's very critical, and Larry mentioned it, you have to know the center of the coordinate system, which is the center of the pupil. Now, I want you to really realize what this problem is. Let's say the center of the pupil is right here, okay? And I'm measuring the elevation of every object in this room, okay? So I'm gonna go over X, and maybe go over Y, and measure the top of Joseph's head. There's an elevation right there, right? Now, if I move over here with my origin, guess what? It's no longer where it was, right? I'm going to get a different answer. My Zernike polynomial will be very different, right? So I was a very strong advocate, and it didn't happen, that the standards had to have how you determine the origin, right? And Larry can give you an opposite opinion here if he wants. And it's basically, no, we're not telling people exactly how to do it. We're only telling people how to specify wavefront error. We're not telling you how to do it. Well, if you want to compare instrument A to instrument B, and the origin is different, you're going to get a different answer, right? Even if you measure the same patient. And that's a problem. Okay. So, and now to the pulsation thing, right? Sure, if the cord is going up and down a little bit, you're changing the versions, hitting the lens and everything. That's why you average. But that pulsation is pretty trivial compared to changes in the tear film. Okay, so you want good measurements shortly after a blink. Now, was there another level of question?
Not that I can remember.
Okay, well, I talked long enough, so you couldn't remember.
The cataract.
Oh, the cataract, absolutely. So she was asking about cataract, Larry, and sure. Yeah, I did a whole bunch of work in cataract, but yeah, the Harmon track, that's why you look at the image. If you have a lot of missing data, the first thing you want to say, oh, this person may have a cataract. I want to go in, got to take care of cataract before we worry about aberrations, right? Right. So it sounds easy, but then, cataracts vary, take them out right away. And you can still measure the aberrations around the cataract. You're just throwing out some of the data. That's why thousands of samples, right? And then you can throw out some data.
Thanks. I'm not sure if it's practical, but could one, in terms of this correspondence problem, could one not color each little lens set, and then the charge coupled device could measure, each unique wavelength or frequency?
Yeah, it's funny you would mention that. My laboratory, along with my colleagues at the laboratory, we have a couple patents to solve things like that. Like we would actually cover some of the sets, so we were sampling less densely and then uncover them. And so you can code, but the most common way is to shorten the focal length of the lenslet and go to a higher density camera. Mhm. Who do I give the mic to?
Yeah.
All right. Oh, we got another one.
Yeah. Currently, okay, in South Africa, to the black community is still less, but how can sorting aberration help in the reduction or elimination of the high myopia that is growing?
Not sure I understand the question. Let me tell you what I think you asked, okay? Like Larry, I'm beginning to lose my hearing, and my wife's sitting back there, and she will tell you very explicitly I'm losing my hearing, and I am. I have to admit it. But I think you ask, given the high myopia, can we actually measure it with an aberrometer? Is that true? Yes. Okay. So I did hear you, right? So you need most aberrometers can measure an diopter error. Okay, that's a fairly high error. Okay, these high dynamic range ones, like you have to measure highly aberrated eyes, they go out to $20. So you can measure. It's just you have to buy the aberrometer that has the dynamic range necessary to measure. and all the aberration structures that come with that myopia. You got more. I didn't answer your question. I can tell.
Here in South Africa, we don't have labs or we are sort of clinicians. Yeah. Will you come and set up the laboratory?
Come and set it up. I'm retired like Larry. No, it takes a lot of work, but the last instrument I showed you is commercially available. So it's very high dynamic range.
No.
But I also consult for them, so.
Researching on it, not clinical application.
Oh, not clinical. Oh, well, yeah, there's a lot of people in this room that probably could set up an apparameter for you. I don't know in South Africa.
We have one at UJ.
Yeah.
Two. We have two.
You know, it's incredible. I think in Houston, there's like 60 of them now, okay, that are in clinical offices, right? So it's happening, and that's a problem, because as I tried to say yesterday, we're not teaching clinicians what's really happening. So you get these phone calls and somebody wants you to answer a question. Like, well, I gotta look at the data. I gotta see that image, and then they'll send you the image, and more times than not, you say, well, you got a bad data. And then they'll say, well, we've tried really hard to get good data, and I'm like, well, unless I'm standing there, I can't tell you exactly what you did wrong. So proper clinical training and getting people it's amazing to me. We teach Snell's law, right? Then we really throw it away, right? It's like you just, if you just walk away with anything from my talks, right? That is the local tip and tilt at every location in the optical system directs the ray, and it goes where it goes. And forget about everything else. Now you have to measure it. And if you don't measure it, then one of my good colleagues and former graduates, Jason Marzek, would say, what you don't know, you don't know. And everything else, you're waving your hand. Go measure. And have an answer. And it's amazing. And working with our clinical patients, one of the first things they'll say, this is the first time someone didn't give me a bullshit answer. Right? It was like, oh, do you have higher order aberrations? And they go, well, what's that? Right? And the patient suddenly thinks you're a jerk, right? But if you measure it and you do a simulated image and you show it to them, even though they have bad, oh yeah, now you're getting to something I see, right? And they have bad optics. And it's always amazing. They look at it, oh yeah, that's closer to what I see right there. So even through their own optics, they can tell when you're representing it closer to what they see. Yeah, my wife's giving me the cutoff ray. You're talking to me. It's nothing like having your wife in the bathroom. Get out of here. Oh.
Thank you, Ray. Thank you, Larry. Next up is the poster session. I see all the posters are up already, which is fantastic. There is also tea, coffee, and some snacks at the back. So maybe grab something and then while you're browsing the posters. Tonight we're going to the Boma for dinner. The truck leaves at 6 trucks. So if we can meet at reception by 5:45 we should be fine. 5:45.
Warm jackets.
Yes, warm jackets. I think we know that. Okay.
It's important. It's one of the
It's good.
Do you know Carlos?